Okay, thank you for inviting me to speak here. And the other important thing is that everything I'm going to say is joint work with Tim Browning and Dan Loughran. And the title looks a little bit like something you might expect in a sociology journal or something, maybe. But anyway. Okay, so what's the situation? I'm interested in families of varieties over a number field. So throughout, K is going to be a number field. And I'm going to have a family of varieties which is going to be over projective space. So I've got a morphism here called pi. And, well, I might say a few more technical details later about what assumptions I need to make on pi. But so let's just say for now it's a family of varieties for the introduction. So the fibers are going to be proper. They're mostly going to be smooth. They're going to be geometrically irreducible, probably. When I write a specific theorem, I will make this more precise. So what type of questions do you want to ask here? Well, you probably want to ask how many B, let me call it P, how many P in Pm of K satisfy, how many of these things actually have a rational point? So how many of them satisfy xp of K non-empty? That would be a nice question to be able to answer. But it's also a very difficult question to answer in general, so we try and answer slightly simpler questions. And maybe I should make a little more precise what I mean by how many here. So the thing about the main reason we've chosen the base to be projective space is that we know how to count points in projective space in a nice way. So really what I'm asking is I want to look at the number of P in Pm of K such that the height of P is less than B and xp of K non-empty. And I want to divide that by just the number of points of height up to B in projective space. And I want to look at the limit of this thing as B goes to infinity. So that's what I really mean by how many. Maybe this limit doesn't exist, maybe it does. If it does, what is it? So because this is difficult, we try and answer easier questions instead. So easier questions. We might ask, rather than being globally soluble, we might ask how many fibers are everywhere locally soluble, so have points in every completion of K. How many xp have xp ak non-empty? So that's a sort of local question. And in order to get a little closer to understanding which ones actually have a rational point, I might ask, for example, how many fibers do not have a Brownian obstruction to the Hasse principle? So how many have xp ak br non-empty? So I'm using the same sort of notation as Olivier used in his lectures. This is the set of adelic points orthogonal to the Brauer group of the fiber. Maybe I should put Brauer xp. If the varieties are, for example, rational, then this is conjectured to be the only obstruction to the hazard principle, and so this would actually be the same answer as the question we're interested in. So the methods I'm going to talk about could in principle answer this kind of question. We decided instead to focus on weak approximation. So how many have, well, you might ask xp of k dense in xp of ak. In other words, how many satisfy weak approximation? Or you might ask how many of them have a Brouwer-Manin obstruction to weak approximation. So that's how many have xp ak Brouwer xp not equal to the whole of xp ak. This is actually the question that we decided to address. And the reason really is, if you have a Brouwer-Manin obstruction to weak approximation, then you definitely don't satisfy weak approximation. So we actually get a concrete statement out of this. We can say this many fibers do not satisfy weak approximation, because as soon as this set is not the whole of this set, well, this set's contained in here, so it's not dense in that one. Whereas the other way, I mean, this is very nice, being able to say how many have no Brouwer-Manin obstruction to the hazard principle, but you can't then conclude that they actually have a rational point. So it's somehow a less satisfying statement. OK, so that's what we're going to concentrate on. Let me begin by stating one of the two theorems, which is going to be the one that I'm not going to talk about. But let me state it anyway. So that, yeah, we also address this question. This question is going to be Theorem One, which I will state and then won't really say any more about. So Theorem One. The same setup, pi from x to pmk. This is going to be a dominant projective morphism. And we need to put some conditions on x as well. Oh, no, we don't for this one. OK. All we need to say is that the generic fiber is geometrically integral, which is a reasonable assumption, because we're interested in families of geometrically integral varieties. So geometrically integral generic fiber. And let's have some hypotheses. So first of all, I need to put a condition on the fibers over codimension 1 points of the base. So those are going to be generic points of divisors on the base. So let's assume that the fiber at each codimension 1 point of PM is split. So this also appeared in Olivier's talks. One way to say this is that it has an open set, a non-empty open set, which is geometrically integral inside it. And let's also assume that there are some adelic points on X. Then the conclusion is that this counting thing, so this limit, which, yeah, maybe I'll write again. So limit b goes to infinity, and then the number of p in pmk such that height of p is less than b, and xp has an adelic point divided by just the number of such p. This thing exists, and it's simply a product of local densities. Okay. Right, so if you look at the author list, you notice that some of us are analytic number theorists and some of us are algebraic people. And this is definitely an analytic kind of a statement. So that's a reason I'm not going to say anything about it. Also, there's a possibility that my co-authors might watch the video at some point, I guess, so I should be a little bit careful. Okay, so proof. All I'm going to say is that this depends on a mysterious thing called the sieve of Ekerdal, which has appeared, so slightly less general statements have appeared in various other places, and this has now been generalized to this. But let me give you an example, and this is a family which will occur again later. Diagonal cubic surfaces. So these are of the form a0 x0 cubed, a1 x1 cubed, plus a2 x2 cubed, plus a3 x3 cubed equals 0. 86% of these have points everywhere locally. Approximately 86% are everywhere locally soluble.
So you have an explicit formula for the local densities?
Yes.
So you can tell when it's 0 or not 0?
Yeah, I mean, you can. There was a paper on these in the 80s by Kolotelen, Kanevsky, and Sansuk, which contains almost all the information you need to work out these local densities. And in any case, it's not difficult working out the.
In general?
Here in general, yeah, I don't want to make too general a statement. Yeah. Yeah, I think probably not. No, because there's any prime there's going to be some conditions for having, even for having a point modulo p, there'll be some. No. Okay, I won't speculate. Let me move on to the more algebraic part. Okay, it's going to turn out that actually that 100% of these ones have an obstruction to weak approximation. So there's 86% that are everywhere locally soluble, and 100% of those fail to satisfy weak approximation. So let me. Yeah. So if you're, so large enough prime with good reduction, then.
So there's no condition for, so if p is large enough, then it's free.
Yeah, it would seem like that. Yes.
No, but there are things that are reducible.
No, that's the whole point of condition 1. Well, unless.
No. The set of reducible things is very small.
Yeah, okay. That's the
But they always, you can't be on them.
But it's, you can perform.
Yeah, so it's, so that's, yeah. So the number of things that have points at mod B goes to 1 very rapidly as people.
Right, yes, there's maybe 1 over p squared of them that land in a bad thing or something like that. Yeah, okay, thank you. Okay, so Yeah. Let me remind you a little bit about the definition of the Brouwer-Manin obstruction, and we're going to need to understand it just a tiny bit better. So let's recall the definition of this set. XAK Brouwer is the set of all adelic points, so that's a collection of points at each place. Okay, let me not call X is going to stay the same thing all the way through. Let me call this Y instead. So it's a set of adelic points such that for all alpha in the Brouwer group of Y, whatever that is, if I apply alpha to PV, take the invariant and add them up, I get 0. So what I want to get from this is, what does it mean to say that this set is actually the whole of this set? That means that this sum is going to have to always be 0. And if this sum is always 0, that means it doesn't depend on these PVs at all. So if I manage to find some place where this invariant in V alpha PV actually depends on what point I chose, then I definitely have an obstruction to weak approximation. So that's the conclusion. So to show this thing is not the whole thing, it is sufficient to find one place V such that in V alpha of PV is not constant on, say, PV in YKV.
What happens if you have another place where the local points is in?
Okay, I'm probably going to assume from now on that I do actually have adelic points everywhere. Yes, thank you. It's how you define what it means to satisfy weak approximation when the set is empty is not entirely clear. Okay, so this is what we're going to do. We're going to show that in order to show things don't satisfy weak approximation, we just need to find one place where this map corresponding to... and I only need to do this for one alpha in the Brouwer group as well. So it's sufficient to find one alpha in Brouwer Y and one place where this happens. Okay. Let me look at the diagonal cubics again. Because for the diagonal cubics, you can actually do this very explicitly without having to develop any more theory. So diagonal cubics. So there's a paper which entirely solved this problem. Koletanen, Kanevsky, Sonsuk. I don't have the year, but I think it's maybe 82 or something. So what did they work out? Let's take Y to be this thing. They showed the Brouwer group of this thing modulo constants. So it's worth pointing out elements of Brouwer K, right? There are constant elements of the Brouwer group of any variety. They play no part in the Brouwer-Manin obstruction because they automatically satisfy this condition. So we can quotient out by them whenever we're thinking about Brouwer-Manin obstructions. So this thing has order 3, except when some special things happen. So except in special cases, and these are things like A1 over A0 is a cube or something like that. So that happens on a thin set. So in particular, for 100% of the members of our family, this is true. And they also showed that if you have an odd prime greater than 3, I guess all primes greater than 3 are odd. If you have a prime greater than 3, and it satisfies, so it exactly divides one of the coefficients, p exactly divides ai, and it doesn't divide any of the others, and p doesn't divide aj, j not equal to I, then this, well, you take either of the two generators of this group, Brauer group, you look at the evaluation map at the place p, and it's not constant. In fact, it takes the values 0, 1/3, 2/3. So then inv p alpha p p is not constant. Okay, and they proved this in a very explicit way. Right, so this happens for 100% of the members of the family. This thing also happens for 100% of the members of the family. That's a little exercise. So we deduce immediately that 100% of these have an obstruction to weak approximation. Okay. So the aim then is to see what's going on here and try and generalize it. I should maybe point out there's a sort of contrast here compared with what Olivier was talking about with the fibration method. So in the fibration method, you have some complicated variety and you're hoping to fiber it into more simple things and understand what's going on. Whereas here, the total space is usually very straightforward. It's a rational variety, and it has points, and we know everything about it. And it's the fibers that are more complicated that we're trying to understand. So it's not too clear in my head how these two things are related to each other, but they seem to apply in different situations. Okay. So it looks like there is a generic element of Brauer Y in this situation causing an obstruction to weak approximation on 100% of fibers. Okay. This turns out not quite to be true, in fact. So generic element, you would think probably means an element of the Brauer group of the generic fiber. But Brauer group of, so let me go back to calling this thing X, this family, and eta is the generic point of PM, P3. Problem is that the Brauer group of X eta modulo the constants, so let me say eta spec K to PM is the generic point. Now this thing's actually trivial. So this was shown in a nice paper by Uematsu. So it would be really nice if there was some generic Brauer element on this family causing these obstructions. But actually, this is not true. And let's understand exactly what's going on. Well, okay. What's going on? So if Y is, say, a smooth, proper geometrically integral variety over K, a number field, well, okay, over K. It might temporarily not be a number field, but let's see what happens. Then there's a spectral sequence which comes from the Hochschild-Sayre spectral sequence, which says that you have the natural map from brow K to brow Y. I'm going to put brow 1Y. So brow 1Y is the algebraic part of the brow group. These are things that it's the kernel of the map from brow Y to brow Y over K bar. This lands in here. And the next thing here is H1K pick YK bar. And the next thing is H3K K bar star. Okay, and in the nice case when K is a number field, this H3 is 0. And so every element in this is something nice and straightforward and easy to calculate. This is, at least in the situations we're interested in, a finitely generated free Z module with a Galois action. You can compute this very easily. And then you get a description of brow 1 modulo brow K. So in the number field case, this goes away, and that's fine. And you can compute this, and you find, this is the calculation they did, you find that it's Z mod 3Z, usually, and you deduce that this quotient has order 3. However, if you go to the generic fiber, where, say, replace little k with capital K for this particular family, then it turns out this map, this is still order 3. It's exactly the same calculation as it is when you work on a general element of the family. This is still order 3. This is no longer 0, and this map here is actually injective. And so, right, this is where Uematsu gets this result that the Brauer group of the generic fiber is actually trivial. Elements of Brauer groups do not specialize in a nice way. Maybe the way to think of this is that when we study these things, when you study a Tel cohomology, you almost always want to work with such finite coefficients because things behave very nicely. Things specialize nicely in families, proper base change, all of this kind of stuff. The Brauer group is not a cohomology group with finite coefficients. It's a cohomology group with coefficients in Gm, and those things just don't specialize nicely. Same if you look at Picard groups in families. They don't specialize in a nice way. Okay, so if we're going to try and answer or try and generalize statements like this, we need to be able to not only treat elements of the Brauer group of the generic fiber, or even though that's easier, we really need to be able to treat elements of H1 of the Picard group of the generic fiber in sort of the same way. And from the algebraic point of view, that was definitely the most challenging part of doing this. So to prove the statement I'm about to write up for elements that really lie in the Brauer group as a generic fiber was fairly straightforward. To extend it to things that don't pull back to the Brauer group was a little bit more complicated. Okay, halfway. Right, let me state the theorem. So theorem 2 is essentially the generalization of this as far as we could generalize it. So we're going to take pi from x to pm over k. X is going to be smooth, projective, geometrically integral variety over k, and pi is going to be flat and surjective. Probably any sensible definition of family has those. And the generic fiber is going to be geometrically connected and it's going to have torsion-free Picard group. Okay, torsion-free geometric Picard group. So eta bar means the inclusion of spec capital K bar. It's a geometric generic point. So pic x eta bar is going to be torsion-free. Okay, and these things are things that then spread out nicely. So this means the majority of varieties in my family are also going to be geometrically connected and have torsion-free Picard group. In fact, all of them turn out to have torsion-free Picard group. Now we need to make a whole bunch of assumptions. So first, some easy ones. So let's assume that we have an adelic point on the whole of X. The whole question's uninteresting if we don't. And let's assume that there is an element somewhere which might possibly give us an obstruction to weak approximation on the fibers. So let's assume that either Brauer group of X eta modulo Brauer group of capital K is non-zero. That's the case where we have a genuine generic element of the Brauer group. Or this H1. So H1 capital K pic X eta bar is non-zero. We can handle either case. So this is going to be the element that gives me an obstruction to weak approximation on fibers. I need to assume some geometrical things. So let's assume that the codimension 1 fibers, so the fibers over codimension 1 points of the base, are, I'm going to assume they're geometrically integral, which is a little bit stronger than we would like, really. But let's assume that. And I also have to assume something about the codimension 2 fibers, which is a little bit strange, but it really seems essential to the way the proof works. So codimension 2 fibers, I don't need to assume much. I just need to assume that they're at least smooth somewhere. So that's the same as having at least one component which is reduced. Multiplicity 0, multiplicity 1. Okay. So they contain a component of multiplicity 1. Geometrically, right, have a geometrically reduced component. This is simply that at some point in the proof, I have to restrict to the smooth lockers of pi, and I want there still to be something there over the codimension 2 points. Okay, and now we have a bunch of conditions that, so we have some element here that we're hoping will obstruct weak approximation. There are a bunch of ways you can construct sort of trivial elements which are obviously not going to obstruct weak approximation. And so we want to rule those out. So let's rule these out. First of all, I want H1 little k pic X little k bar to be 0. So X itself, as a variety of a k, doesn't have any algebraic Brauer group. I mean, in all the examples, this is going to be pretty automatic, because the total space is just some nice variety that's rational over k. So this isn't actually much of a restriction. I also want it to have no Brauer group over the algebraic closure of k. Again, that's almost always going to be the case. And then there's a slightly strange one. Yeah, thank you. Slightly strange one, but one which is definitely necessary, is that if I look at the... So there's a map from the Picard group of Pm up to the Picard group of X, just pi upper star. And that induces a map on Galois H2s, and I want that to be injective. So let me write it. H2 little k pic P M k bar to H2 little k pic x k bar is injective. This is actually sort of, because if this thing has a kernel, then we end up with elements of h1 little k is in the Picard group of the generic fiber, which we don't want, because the conclusion is not going to be true for those. So this looks a bit weird, and it's definitely necessary, but it's actually not too bad at all. Okay, the cubic surfaces has been erased now. But typically, think of the cubic surfaces. That is a hypersurface in P3 cross P3. And that means by the Lefschetz hyperplane theorem that its Picard group is the same as the Picard group of P3 cross P3, and that this pi star map, this is pi alpha star, is then just the inclusion of one factor. So in that case, this map's definitely injective. And that kind of situation seems to, in many examples, you're in exactly that situation. So this is really not too bad. So conclusion. Then for 100% of the points in, well, 100% of the ones where the fiber is everywhere locally soluble, there is an obstruction to weak approximation. So if P in Pm of k intersect pi of x ak, that's just a fancy way of saying the fibers that are everywhere locally soluble, xp has, or fails weak approximation. Oh, and maybe, okay, they're mostly smooth as well. So we're interested in the structure for smooth fibers. Okay, so they're smooth and they fail weak approximation. Okay, so yeah, maybe I should point out this is really some generalization of the diagonal Cubix thing that we had. We didn't have a non-trivial element here, but we did have a non-trivial element here. Codimension 1 fibers, well, for the diagonal Cubix, if you just set, for example, A0 equal to 0, then what you get is a cone over a cubic curve, and that is geometrically integral, so that's okay. Codimension 2, if you set 2 of the coefficients equal to 0, you get a triple plane, which does indeed have a geometrically reduced component, so that's okay. And all of these things simply because because the total space is a rational variety, you just sort of eliminate one of the coefficients and you can see that. And this thing, because as I said, it's a hypersurface in a relative projective space, and Lefschetz hyperplane theorem tells us that this thing is going to be injective. Okay. So I now have 20 minutes to tell you something about the proof of this theorem. Any questions about the statement before I move on to saying something about the proof? Yeah, go on, Ronald.
What's the difference between this 100% and the 86% that this 14% is not locally solvable?
Yes, exactly. Yeah. Okay, I need to tell you something about residue maps in order to go through the proof of this. So let me tell you briefly. Something about residue maps. Let's take Y, a variety, smooth variety over K. And residue maps are a thing that let you decide whether, if I have an element of the Brauer group of an open set, whether it extends to the whole thing. So we'll take Z inside Y, a prime divisor. Then whether a class in Brauer group of Y take away Z extends to brow Y is controlled by a residue map. This is actually the same thing as we've already seen in Alena's talk, a special case of that. And what does it do? It goes, I'm going to call it partial Z, and it goes from the Brauer group of Y takeaway Z, and it lands in H1 of the function field of Z with values in Q modulo Z. I'm saying something slightly weak here. If Z, for example, is regular, it actually lands in H1 of Z with values in Q mod Z. But we don't want to assume that, so let's just say that. And given this, there is then a purity theorem proved by Grothendieck for the Brauer group. And that says that so I can, if I look at this over all of the prime divisors in Y, I can use this to compare the Brauer group of Y to the Brauer group of its function field. What shall I call it? So if I take all the codimension 1 subvarieties of Y, then the things that have 0 residue at every, I guess I only define this on Brauer Y takeaway Z, but yeah, you can extend it in a natural way to the Brauer group of the whole function field. So the things that have trivial residue everywhere are precisely the ones that actually belong in the Brauer group of Y. And I encourage you to think of this as the relationship between rational functions and regular functions. So if you have a rational function, you can look at its valuation on any prime divisor, and it's regular precisely if it has valuation 0 along every prime divisor. It's really completely analogous to that. Okay, so in our situation, thinking about this family and its generic fiber, I can do exactly the same thing to relate the Brauer group of X to the Brauer group of the generic fiber. And what do we get? We get the Brauer group of X, Brauer group of the generic fiber X eta, and then we also get a map here, a bunch of residue maps. So to be in the Brauer group with the generic fiber, that already means that it's unramified at all of the horizontal divisors in X. So divisors in X come in two sorts. There are the horizontal ones, which map surjectively down to the bottom, and there are the vertical ones, which do not map surjectively down to the bottom. And the horizontal ones are the same as divisors on the generic fiber. So something here is already unramified at all the divisors on the generic fiber, so all the horizontal ones. So here I just need to put the vertical prime divisors. Okay. So the idea is that if I have an element of the Brauer group of the generic fiber, and I'm assuming the Brauer group of X is trivial, then this thing must be ramified along some vertical prime divisor. The condition I put on the codimension 1 points means the vertical prime divisors really just are the inverse images of prime divisors down below. So you can think of this as just being the pullbacks of divisors below. I'm not going to, at the moment, I'm not going to talk about the H1 thing. I'm just going to talk about the case where we have an element of the Brauer group, because there the theory is sort of much clearer. It's much clearer how it works. So the first step is to say, okay, if I have an element of this, a non-trivial element of this Brauer group, then it really it has non-trivial residue somewhere. Actually, I need to use a slightly different residue map here. Where shall I put it? Let's do it here. I can go from this, so Z is my prime divisor. I can go up to Z base change to the algebraic closure of, what do I want to say? Right. Okay, here's PM. Here's a divisor in PM. And up above, right, here's X. And up above, I have this vertical divisor in X. So I'm really interested in the generic point of Z. I'm really interested in the generic point of D and in the generic fiber of Z over that. So I'm actually going to be interested in what happens when I map to H1 of K of Z over the algebraic closure of the. So this is sort of, right, this is take the generic fiber of Z mapping to D and then put a bar over the top of it, go to the algebraic closure of the field that's defined over. Okay, yeah, this is a subtlety which is maybe slightly annoying, but I'm really actually interested in this thing, which maybe I'll call partial Z with a bar over the top. Right, so a slight generalization of what I just said says that the things that map to 0 under all of the D bars are precisely the things that come from Brauer group of K. So they're the things that come from below. So if I have a non-trivial element of Brauer x eta, then it has to map to something non-zero in here somewhere. If I have a non-trivial element of Brauer x eta modulo Brauer capital K, that ensures that it maps to something non-zero in one of these, which is what I need to make the proof work. Okay. I need another thing about residue maps. Yeah, I'm going to have to get rid of this. Which is now, let's think temporarily about instead a variety over a local field. So if y over kv has a model y over ov, say, this is the ring of integers in kv, then if I assume that the special fiber here is geometrically irreducible, then that's a prime divisor on curly y, and I can apply exactly the same thing, and I get a residue. And what do you get from that? You get the map from the Brauer group of y to h1 of the function field of what I'll call y0. So y0 is a special fiber. Q mod z, where, okay, this doesn't really mean Q mod z because bad things happen at P, where P is the characteristic of the residue field. But let's overlook that for now. So I get one of these things as well. And I can sort of play the same trick in that I can base change this to y0 bar as the base change of y0 to the algebraic closure of the residue field. And I can go to there. And let me call this thing delta bar. So the fact that I'm going to use to prove the theorem is that if I have an element of Brauer y whose image under this delta bar is non-zero, then at this place, the evaluation map coming from this element of the Brauer group is non-constant, and in fact is surjective. as long as the residue field is large enough. All the way through this, I'm going to be allowed to throw out sort of finitely many primes, so I can always assume the residue field is big. So what we need is a lemma. So this has just appeared in the last couple of weeks. That if you have alpha in Brauer group of Y, such that this delta bar of alpha is non-zero, and the residue field is large enough, then this invariant map, invariant alpha PV, is non-constant on Y KV. Like so many things, this is essentially a theorem that comes down to Langevin. You need to show that certain torsors over Y0 have points, and Langevin does that when the residue field is off. Okay, so now how do the steps of this proof work? Let me write down the steps. So, first thing, let's do the Brauer group case, not the H1 case, because it's a little bit easier. So first of all, any non-trivial alpha in Brauer x eta mod Brauer k satisfies, it's got non-zero geometric residue at one of these vertical divisors. So there's a vertical prime divisor z in x such that delta z bar of alpha is non-zero. Okay, so this element of the Brauer group of the generic fiber is somehow ramified along this prime divisor in X. Now, the second step is we want to make use of this. So if I have a point in the base, PM, and the fiber over it is smooth, so that's one of the fibers I'm actually interested in studying weak approximation on, it's still possible that when I look modulo P, the fiber will not be smooth. And when that's going to happen is when the point I picked in the base, when I consider it modulo P, lands in one of the divisors in the base where some kind of bad reduction happens. So let me write, as over there, let me write D is pi of Z. So if P in the base, PMK, is such that the reduction of P at some place V lands in D. I hope it's reasonably clear what this means. I just go to projective space over the ring of integers, and then this divisor D spreads out onto a divisor on that. And I mean the closure of this point meets the closure of that divisor somewhere. But I mean, just take the coefficients, reduce them mod P, see if it lands in the divisor. It's just the same thing. Well, then what I end up with is the fiber at P is going to be smooth, but its reduction at this particular place is going to be singular, and I'm going to be in the situation of the lemma, just by some commutative diagram property, which I won't draw. So then the lemma shows that xp has an obstruction to weak approximation, and it's given by the restriction of this class. So given by specialization of alpha. Then the final step is to say that actually 100% of the points have this property for some v. So this happens at some v for 100% of points in PMK. So the way that I think of this to myself is we've got a divisor that we're interested in, divisor in PM that we're interested in. And so modulo P, the Langevin estimates say that this divisor contains about 1 over P of the points of projective space. And so if you want to not land in it, then you've got a 1 minus 1 over P chance of doing that. And if you want that to happen at all of the places, that means you should take the product of 1 minus 1 over P over all primes. And that's 1 over zeta of 1, which is 0. Now, apparently, my analytic colleagues tell me that's not really a proof. But it sort of gives you the right vague idea. This is actually proved using a variant of the large sieve. And please don't ask me about that. It's worth saying that the property really depends on this D being codimension 1. As soon as you have codimension 2, then you're trying to land in something that just only contains 1 over P squared of the points, and then that doesn't happen very often. Okay, so that's how the proof works. Let me just say for the étale cohomology enthusiasts that the main problem here is doing the whole residue map thing where you start not with an element of the Brauer group of the generic fiber, but just with an element of H1. And how does that work? Well, you shouldn't think of it as being an element of H1 pick, because the Picard group of the generic fiber was torsion-free. So we can write down look at the multiplication by n map on it. And see that actually elements of n torsion in H1 pick actually come from H0k with values in pick x eta bar modulo n. And this is something that you would very much like to think of as sitting inside H0 of k with values in H2 x eta bar, values in mu n. So actually, it turns out you can extend residue maps to this group. And this actually covers both cases, because this also has a natural map from the Brauer group of x eta, or the n torsion in the Brauer group of x eta. There's some lifting thing involved. It's closely related to the n torsion in the Brauer group of x eta. Okay, so if you manage to define residue maps on this thing, then you handle both cases at the same time, without too much trouble. So that was, I'm very happy to tell people about the algebra that goes into this on another occasion. Okay, thank you very much.